This is section 9.8 power series. In section 9.7, you introduce the concept of approximating function by Taylor polynomials. For instance, the function f of x equals e to the x can be approximated by its third degree Maclaurin polynomial given by this. In that section, you saw that the higher the degree of the approximating polynomial, the better approximation becomes. We didn't explore that, but I mentioned it. I said if we kept taking the n, getting higher and higher, approximation becomes better. In the next two sections, you'll see that several important types of functions including f of x equals e to the x, can be represented exactly by an infinite series called a power series. So it's not the approximation that comes out exact. For example, a power series representation for e to the x is given by e to the x equals 1 plus x squared over 2 factorial plus x to the third over 3 factorial all the way up to x sub n over n factorial. It says for each real number x, it can be shown that the infinite series on the right converges to the number e to the x. Before doing this, however, some preliminary results dealing with okay. Okay, power series. Here's our definition of the power series. If x is a variable, then an infinite series of this form, a sub n times x to the nth power. And you see it changes here. That's x to the 0, x to the first, x squared, x to the third, all the way up. And then the numbers would change in front. That's called a power series. More generally, an infinite series of this form kind of is the same as that, except for instead of x, it has x minus c because it's centered at c, where c is a constant. Okay, let's see. And the instructions here say state where the power series is centered. Well, if we go back to our definition, the part where it's talking about centered, it says centered at C. So we want to rewrite the x as x minus a number. Put in there such I don't change its value. 0. Because x minus 0 is x, x to the nth power is the x to the nth power. So this is centered at 0. Number 7. That was it. Oh, really? I don't think these are too tough at first, and then they get horrible because you have to use a whole bunch of different methods we looked at on them. Now, putting our focus on the x minus, where's this one centered at? 2. And so that's our answer.
As long as you have something that's x minus something to the n, that's when you use it.
Right. For this section. Now, if it's not even a power series, you can't say that. This was a ratio test from sometime in the past. Now, next thing they're going to ask us to do is find a radius of convergence. Yeah, I don't think I got any problems. No, I just put down the steps. So let's go look at problems in the book. The idea is, that we're looking at this, and we got our c, like our x value, and then we got our radius of convergence, where it's converging upon the value. What we saw as approximation in the past, and what we're going to see is we take n even higher, it comes out more exact. And if you took it to infinity, then it come out perfect. But that's what we're talking about, the radius of convergence. That's what big R represents. Okay, so if we look at number 9, and I'm going to have Calc Chat open up to help us guide us for the oddball ones I don't identify. Okay, so this one looks like we just plug it straight into the formula. Some of these, you don't use that formula. Because you have to identify the series as geometric. So you use a different technique for it. That's why I say it's simple at first, but then it gets... what that's doing. Okay. I wonder if the geometric would even work if I use this. But, okay, so we want to find this this limit. So L is going to equal the limit as n goes to infinity. The reason why I put the ratio test on that slide up there is because this is a ratio test, isn't it? The formula, where we plug in n plus 1 and n. Well, same principle here. So if I plug in n plus 1, I'm going to have negative 1 to the n plus 1, x to the n plus 1 over n plus 1 plus 1 over, and then this is just my negative 1 to the n, let's see, x to the n over n plus 1. Now, what will happen to those negative ones? Yeah, they'll cancel away. And the reason why is I could separate these in this manner. Because if you have these multiplied together, multiplication you can split up into two separate absolute values, couldn't you? And no matter what this gives you, 1 to a power gives you 1, right? You throw negatives in there, you have a negative, but then the absolute value makes them positive. So 1 over 1 would give you 1. That would drop away. And over here, I got x to the n times x to the first. We split up the x to the n plus 1 over n plus 2 times, flip the bottom, n plus 1 over x to the n. The x to the n's would cancel. And we got x here, x to the first. I could take that and put it out in front with an absolute value around it. And that leaves us n plus 1 over n plus 2. Why can't I just put that out in front? We know we can take numbers and put them out in front. Our limit is based upon n, isn't it? And since this is all multiplication, this is not going to be affected by n going to infinity at all. Now, what rule could I use here? L'Hopital's rule? Yeah, so that would give us 1. Now here, it's going to give us some value. Specifically, it gives us x. It's not infinity, and it's not 0. So if it's not infinity, it's not 0, it's going to be this case. And this is where you take the absolute value less than 1 and figure the radius. So what would our radius be? 1. Because from college algebra, this would become what? Negative 1 is less than x is less than 1. Here's our c. This would be negative 1 to positive 1. And that's our radius of convergence. And that's what where we're headed with that. Does that make sense how to find that radius of convergence there? Let's take a look at number 11. And infinity for the 4x to the n power over n squared. Okay, so let's find our limit here. So limit as n goes to infinity of the absolute value. And on top one, we're plugging in n plus 1 for the n. So we're going to have 4x to the n plus 1 over n plus 1 squared over 4x to the n over n squared. The top part, I'm going to rewrite that as 4x to the n power times 4x to the first power, because we can split up the n plus 1 in that manner. This will be n plus 1 squared times, flip the bottom part. That's n squared over 4x to the n. Four x to the n powers cancel. The 4x I can bring out in front because it doesn't have anything to do with the n. but I have to keep the absolute value around it. Can't drop that. And I'm left with n squared over n plus 1 squared. Now, if I were to FOIL this, it gives me n squared plus 2n plus 1. I'd have an n squared here and n squared here. If I kept taking the derivative using L'Hopital's rule, what would this equal? 1. So that gives us this, which is a value. It's not 0 and it's not infinity. So that tells us if we have a value, then we plug that value in here. So we got the absolute value of 4x is less than 1. Oops. Now, if I were to solve that from college algebra, this would be our P. I'll give you the formula. This is our Q. P is always what's inside absolute value. Q is the other side. Our formula says negative Q is less than P is less than positive Q. So if I plug those in, I'd have negative 1 is less than 4x is less than positive 1. Divide everything by 4, and I get negative 1/4 is less than x is less than positive 1/4. So what would my radius be? 1/4, exactly, because the zero's in the middle. So the difference between the middle and one of those edges is 1/4. Now, if you're wondering why is it always less than 1? The condition of convergence is this column, and our ratio, remember, was when it's less than 1. So that's why when you're doing a ratio test, you set it less than 1 if you got a value. That's based upon this. Is this one any different? Let me see. Just got a factorial. Let's do that one. Number 13. Okay, so we want to find this limit. Limit as n goes to infinity. And we'll plug in our n plus 1 on top. So we got x to the 2 times n plus 1 over 2 times n plus 1 factorial over, and I should have looked to make sure this wasn't like the geometric, or didn't look geometric. So we got limit as n goes to infinity. Top part, that becomes x to the 2n plus 2, multiply the 2 through, and multiply through here, and I get 2n plus 2 factorial, times, and I flip the bottom part, that's 2n factorial over x to the 2n. So my limit as n goes to infinity, this breaks down as x to the 2n times x squared. And this is 1 times 2 times all the way up to 2n. And then 2n plus 1. and then 2n plus 2. Because that's what 2n plus 2 factorial represents. Times 2n factorial is 1 times 2 all the way up to 2n, and then x to the 2n. Now this x to the 2n cancels that x to the 2n. 1 times 2 all the way up to 2n. Oops. That cancels with that. And actually, I can bring that x squared out. So I got the absolute value of x squared, although x squared is always positive, so I don't need the absolute value on it. Limit as n goes to infinity. Nothing left up on top, so that's 1 over 2n plus 1, 2n plus 2. Which if I put infinity in for n, what's the denominator going to be? Infinity? 2 times infinity plus 1 times 2 infinity plus 2. Well, that's what's going to give you infinity 1. So 1 over infinity gives you 0. 0 times the x squared gives us 0. And if L is equal to 0, then your radius convergence is infinity. Now, when it's equal to infinity, it says, therefore, by the ratio test, the series diverges and converges only at its center. So radius convergence R equals 0. I write that down right? I'm looking at the wrong one. Let's see, look at the correct one. Here it is. For any fixed value of x, this limit is 0. So by the ratio test, the series converges for all x. And therefore, the radius convergence is R is equal to infinity. It'd be nice if they showed a picture of this. I don't think they do. No, they don't. Questions on finding the radius to convergence? Okay, so now we've got a radius of convergence. We found that, and the interval is easy to get. For example, if I had like this right here, my interval would be -1 to +1. That's your radius of convergence. The question that comes in is what's happening at -1 and what's happening at +1. And that's what this next topic talks about, is looking at your endpoint convergence. And I think this is a challenging part, because once you plug in those values, it becomes a different type of problem. And it might be a p-series, it might be a geometric series, and you have to have that sheet in front of you because it could be any one of them. So that's why I said it's a little bit the challenging part. Like here, we come up with an example, and it's equal to the absolute value of x, which you said less than 1, so your radius is 1. So you know it's converging from -1 to 1. However, you don't know about the endpoints. And so what you do for like x equals 1, you plug in 1 for x, and you take a look at what it does. This one would be a divergent harmonic series. So this is a harmonic. Here you plug in -1. And when you plug in -1, this becomes a convergent alternating harmonic series. And that's why I copied this table here. And we'll use CalcChat because I don't want to sit there and flip through and try to find it. This will guide us from exactly which one to look at. Problem. Does that make sense? The idea of what we're doing? So we've got our interval, we just got to decide the endpoints. Let's take a look at number 15. I think this is one of those bizarre ones. They make the note that the series is geometric. Let's see, geometric. I guess it would be. So if it's geometric, this would be our R, wouldn't it? So that'd be our R. And it says where it converges is where the absolute value of R is less than 1. So we have x over 4 is less than 1. Which becomes -1 is less than x over 4 is less than 1. Multiply by 4, and we got -4 is less than x is less than +4. So we know that's where it's converging. Now, you notice that they don't say anything else. You know, they don't check the endpoints or anything because this is geometric, and our geometric specifically says less than. There's no line underneath here, is there? Since this is a less than, then that means these have to be parentheses. So that's our interval of convergence. The question is, could I have went through the other process and come up with the same result? Are they just showing us a shortcut, or do we actually have to identify that as geometric? So I'm going to come over here. I'll find my limit. As n goes to infinity, I plug in n plus 1. So I got x over 4 to the n plus 1 over x over 4 to the n. And I'm just going through the same thing we've been doing. And the top part I'll break apart as x over 4 to the n power times x over 4 to the first power. The x over 4 to the n powers would cancel. Now, that leaves us the absolute value of x over 4, and there's no n left, is there? So it doesn't matter about the n. This is going to give us x over 4 inside the absolute value, which is a value. And this says if you come up with a value, then you take the absolute value less than 1 and figure the radius. Which happens to match this over here, right? So we get negative, I'll skip some steps. It's already got written over there. Negative 4 is less than x is less than positive 4. Then the question becomes what's happening at the endpoints? You know, what's happening here and what's happening here? So I'm going to examine that. And I'm going to examine at 4. Now, when I say examine them, I'm going to plug them back in to my original problem here. So I'll be plugging in negative 4 for the x. Close to my original problem. Let's see, negative 4 to the n. And over here, I'll be plugging in, for my x, I'll be plugging in a positive 4. Okay, they both have n powers, so those are geometric series, aren't they? The a to the Rn power. So if I look at that, this would be my r, which would be negative 1. And this would be our r, which is a positive 1. Again, what identified that is I started looking through here, looking for something to the n power. And that's where I saw the geometric series. Well, if I take the absolute value of it, it's going to be this right here, right? Greater than or equal to 1, which means it diverges at the endpoints. When we say it diverges at the endpoints, that means that we have parentheses on. Converges would mean we put a bracket, means it includes that value. So I guess you don't have to recognize right from the very beginning it's a geometric series. If you go through those steps, at least that one will give you the answer. Again, this is where I find it challenging because when you plug in your x value, it may turn into all kinds of different forms down here. Questions on that problem? Okay, let's take a look at number 17. N equals 1 to infinity, negative 1 to the n power, x to the n over n. Now again, we're back to these right here. So we need to find this limit. So limit as n goes to infinity, absolute value, I'll plug in n plus 1. So I got negative 1 to the n plus 1, x to the n plus 1 over n plus 1, all over just this. negative 1 to the n, x to the n, n. Okay, so the top part, I'll split it apart a little bit. So I'm going to have negative 1 to the n times negative 1 to the first power. I'm going to have x to the n times x to the first power. Bottom part will be n plus 1. I'll flip the fraction down below, multiply it times the top. So n over negative 1 to the n, x to the n. Negative 1 to the n, negative 1 to the n cancels, x to the n cancels. Guess that's it. So now here I got negative 1 to the first power. But again, I could split that apart. I could have the absolute value of negative 1 to the first power times all the rest. And basically that negative would drop away, wouldn't it? And that's because it's multiplication. Let me write that out. This negative 1 here, I could put in its own absolute value bars. Reason why is because if you have the absolute value of x times y, that's equivalent to the absolute value of x times the absolute value of y. That's only true when everything's multiplication. If there's a plus in here, you cannot do that. So I can split these up. And so then I'm left with, what am I left with? X over n plus 1 times n over 1. Yeah. And again, absolute value of negative 1 becomes a positive 1. That drops away. This x here has nothing to do with the n, so I can put it out in front with an absolute value around it. And we got n over n plus 1. And we sure use the L'Hopital's rule a lot, aren't we? Oh, they are. Oh. Okay, so that goes to 1, and then well, that's just 1. So we got this, which is a value. So if you get a value, this says that you're going to set less than 1 and then figure out the radius and your interval. So this will go from negative 1 to positive 1. So I know my answer is going to be negative 1 to positive 1. What I don't know is what's happening at the endpoints. So for the endpoints, I need to check. I'll plug in negative 1, and I'll plug in a positive 1 into our original problem for x. Our original problem was this, summation n equals 1 to infinity, negative 1 to the n, x to the n. So this will be negative 1 to the n over n. And this one will be n equals 1 to infinity, negative 1 to the n, and plug that in for x, and our function was x to the n. So I got 1 to the n over n. Now here, this becomes negative 1. Negative 1 to a power times negative 1 to a power, you add the exponents. N plus n. Now over here, what's 1 to any power? 1. So this 1 to the n power is going to drop off. So we're going to have negative 1 to the n power over n. Now, n plus n is 2n. n equals 1. 2n becomes 2 times 1, which is 2. N is equal to 2. 2n becomes 2 times 2, which is 4. The next one would be 3. 2n becomes 2 times 3, which is 6, which is always an even number, isn't it? What happens to a negative number when you raise it to an even power? Negative 1 squared, negative 1 to the 4th, negative 1 to the 6th. It always becomes positive. So this becomes a positive 1. And here's the part where I may have to treat chat. But let me see if I can spot them. I think this, I don't know what this is. It's always the first power. I think that was a P series, wasn't it? Yeah, P series. So like on this one, where this is the first power, that's in the form of a P series, and where our power, P, is equal to 1. And what that tells us is when P is equal to 1 for the P series, that's the conditions of divergence. So this diverges. What that means is there is a parentheses on negative 1. This one alternates. First off, it can't be the P series because the P series doesn't have a number in front of the n, does it? Doesn't have a number on top. I can't take the number out in front because the n is dependent upon the summation. So I'm looking for something to the negative 1 power. Alternating series, would that be? Is it on the page right now, or I'm not looking at it? Let's see, what problem is this? Oh, cheat, 17. I'm not very good at identifying. I wouldn't lie and say I was. What do they say to use on that one? Alternating series. Isn't that where we were? That's a good question. It's not exactly like that, unless the alternating series in whatever section that was in had two forms. Was there? Okay. Well, either way, I know this was the same for convergence. For the alternating series, both of these had to be true, which means we need to check to see if a to the n plus 1 is less than or equal to a sub n, I should say, not 2, and limit as n goes to infinity of a sub n equals 0. So both those have to be true. Let me see. Plug in n plus 1. I got negative 1 to the n plus 1 over n plus 1. And this would be negative 1 to the n over n. So this I can rewrite as negative 1 to the n times negative 1 to the first power. Okay, that one's got me puzzled. Because I show it diverging, but they say it. Oh, no, they say it converges. They just have negative 1 to the n power. Oh, did I plug in my x value? I did, didn't I? Yeah, negative 1 to the n. Do you see anything wrong I've written here? If I plug in 3, for example, negative 1, 3 plus 1 is 4, right? And then here I'd have 3 plus 1. And this has to hold true. If I plug in 3 over here, negative 1 to the fourth power is positive 1. That gives us 1/4. Negative 1/3 power is negative 1. That's not true, is it? And our rule says that has to be true for all values of n. Interesting. Well, I disagree with their answer. I don't see how it can, because when this is n plus 1 and this is n, there's going to be times when this is positive, there'll be times when this is negative, and it'll be the exact opposite of this. So there's no way that holds true. So it fails. So my claim is the book screwed up, and that should be a parentheses here. Interesting. Mind you, they have people coming up with those keys, so they do make mistakes. Unless you see something I've written down wrong right here. Ooh, it's 9:09. I'm not going to be able to finish this section. That's probably not a bad place to take a break. Take a break until next week. So we'll go ahead and stop there. I'll put a quiz out there from the material we did last time. So, and then next time we'll finish this section, and then we'll go on to 9.9.
What was the stuff we'll be covering?
That'll be the main thing we did last time was the ratio and root tests.
Okay. Can you name that on the quiz? Just name it ratio and stuff like that. That way I can study that before I take it.
If I remember. But if I don't remember, just go ahead and like put it in your phone right now or something. That's ratio and root test. What are we over? Oh.